I think we move to the presentation by Homam Spartali, who is a PhD student at Aachen Universität, so Aachen University in Germany, in the Institute of Structural Concrete. And the topic is the bond behavior between high strength concrete and steel reinforcement and the high cycle fatigue push-in loading. So please, the floor is yours.
Hello, everyone. My name is Homam Spartali. I work at the Institute for Structural Concrete in RWTH Aachen University in Germany. And I would like to thank you all for being here and welcome you to my presentation with the title Bond Behavior between High Strength Concrete and Steel Reinforcement under Monotonic and High Cycle Fatigue Push-in Loading. When talking about bond behavior and bond fatigue, the first thing that may come to one mind is this test setup with a pull-out load. This is totally understandable as we usually use steel in reinforced concrete structures in tensile zones. However, because of the demand for renewable energy, structures that may subject to alternating loading has been developed, like wind turbines. In these structures, this alternating loading can trigger compression stresses as well as tension stresses in the same reinforcement rebars. That means that both cases, the pull-out case and the push-in test, and the push-in load state needs to be investigated, because in the push-in case, we may see different bond behavior or bond stress profile along the bond zone. These type of structures also subject to high cycle loading, which may be more than 10 million load cycles through their lifetime. So in this research, we considered this also. And because of the increasing high utilization of high strength concrete, we also used concrete mixtures up to a compressive strength of 120 megapascal. Now let's see the gradients of our specimens, namely the material properties. So we use two classes of concrete according to the FIB model code. These are the C80 and C120. And according to the material tests that accompanied our push-in specimens, we obtained the value 84.2 megapascal and 107 megapascal for the first and second concrete class respectively. Regarding steel, we used the class B500B with a tensile strength of 500 megapascal, and we used two different bar diameters. The first is 25 millimeters and 16 millimeters, which are also ribbed bars. Now, the most common test for bond behavior is the Ryland pull-out test. However, it was found that this test overestimates the bond strength because of these compressive stresses that emerge while loading. That's why we used another test setup that is mentioned in the ASTM, and it's called the beam end test, which ensures that these compressive stresses locate outside the bond zone. But we have here another problem, that in our case, we need to apply push-in loading from this side, and that could produce bending or buckling in the rebar from this side in the case of beam end test. So we had to introduce a void or a recess inside the body of the specimen so we can apply the load directly on this end of the bar. In this figure, we see also the reinforcement that we used and the concrete cover and the dimensions of the specimen that were taken relative to the bar diameter, this bar diameter DS. The specimen was subjected to the loading in this vertical orientation. And this was the most prevailing failure mode, with 2 transversal cracks and 1 longitudinal crack along the bond zone. And regarding measurements, we use 4 LVDTs, 2 to measure the slip at the loaded end and the unloaded end, and 2 to measure the width of the cracks, width of the longitudinal and transversal crack. Now talking about the testing campaign, so we had a total number of 44 specimens, among were 29 tested in as monotonic tests and 15 were tested to fatigue tests. Now, this is not my lucky number or something, 29 and 15 and 44. Actually, this testing campaign is a part of a larger campaign that we are performing at our institute. And the results of the rest of the experiments will be available later when they are finished. Let's see what parameters have we changed. In the case of concrete C120, we changed the bar diameter. So we used the 16 and 25 bar diameters, but we kept the bond length constant, 2.5 ds. However, in the case of concrete C80, we also used another bond length of 5 ds. Now that we know everything about the testing campaign and materials, let's move to the results. In the case of monotonic tests, we applied displacement of 1 millimeter per minute to the end of the bar. And in the case of concrete C80, we obtained the following results for also the diameter 16 millimeter. The green curves are for the bond length 5 ds and the black curves for the bond length 2.5 ds. We see that by doubling the bond length, we almost also double the maximum reachable force, or the bond, maximum reachable force. In this other diagram, we see a comparison between the results for the 2 different bar diameters, 25 millimeters and 16 millimeters from the same concrete and bond length. And in this last figure, we see the result of the concrete C120 for the bond length 2.5 ds and the 2 different bar diameters. Now, by comparing these 2 figures, the red curves in these 2 figures and the black curves, we see that by increasing the bond strength as expected, we also increase the reachable force or the bond strength. Now let's take one curve from each of these groups to look at the effect of the splitting crack. Let me also make a zoom in at these areas marked in red up to a displacement value of 2 millimeters. Now let's focus also on the middle diagram. So at some point of the loading, we will observe this splitting crack that comes along the bond zone. Let's mark this point with this dot in this experiment and this dot in this other experiment. And here we can notice something, that by the emergence of the crack at this point, we see that the bond stiffness directly reduces or decreases, but the force will keep going up until we reach the peak. And after the peak, we will see a deterioration, here also a deterioration in the bond resistance with the rapid increase of the width of this crack. Or maybe I forgot to mention that the axis that we added here is the crack width, which allows us to compare how the crack width is developing with increasing the, or with the increased slip. Now, this behavior was also observed in the other cases with the different bond, and here with the different concrete, C120, we see always this start of the crack and then reaching the top and then the deterioration with the further increase of the crack, of the splitting crack. Now in this figure, we see the bond strength obtained from each one of the monotonic tests plotted against the concrete strength that we obtained from the accompanying material tests. Let's compare our results with the formulas that are available in the model code. In the model code, it's distinguished between two kinds of failure: the pull-out failure, which is given by this equation, and the splitting failure with or without stirrups. In our case, with stirrups, which is represented in this equation and these two curves. It depends on the bar diameters. That's why there are two curves here. And this equation is represented by this curve. We see that in general, the formulas of the model code underestimates the bond strength that can be reached in reality for the case of push-in tests that we did. Actually, for the confinement level and the configuration that we used, we obtained the following ratio between the bond strength and the concrete strength using this line. Now that we saw all the monotonic tests, let's move on to the cyclic tests. Before I introduce the cyclic tests, I would like to go quickly to the idea of fatigue creep curves in the case that someone is watching without fatigue background. So we see this figure that represents the load displacement curve in one of our fatigue experiments. And Fu is the maximum value reached by the corresponding monotonic test. And in this case, we use a maximum load level of 75% from Fu and a minimum of 40% from Fu. If we took the slip at each one of these peaks here, we can plot these with the corresponding number of cycles at each one of these to obtain the fatigue creep curve. Now we can also add a fatigue creep curve for the longitudinal crack. It's to be mentioned here that all the results that I'm showing in this presentation are for the unloaded end. So we just skip the loaded end results for the moment. Now we are able now to compare the fatigue creep curves. In the case of concrete C80 with these parameters, we tested 3 different maximum load levels. And it's to be noticed here that in the first load level, we saw the crack, the splitting crack in the second half of the fatigue lifetime. And in this load level of 75%, it was observed in the first half of the fatigue lifetime. And in this case, the highest case, it was observed directly from the beginning, as we see here from the first few cycles. The second thing that we can notice here is that the slip increases steadily until we see the emergence of the crack, which accelerates the slip value and leads eventually to the failure of the specimen or of the bond. Here's another test which lasted until 12 million load cycles without failing, which had the same parameters of the last slide, but with a diameter of 25 millimeters and a maximum load of 75. Here are the results for the concrete C120 with these parameters. We tested here two maximum load levels, 75 and 85. And in this case, in this experiment, we saw a push through or a pure push through failure. That means we didn't see any splitting crack, which you can also notice here from the line. In this case, we also noticed the same thing, that the emergence of the splitting crack accelerated the slip and led to failure. Here's a comparison between our fatigue results and the SN curves that are provided by Eligahausen, who did a lot of pull-out tests. To indicate here that in our case push-in, in his case pull-out, but here's a comparison. We applied 2 maximum loading levels in the case of concrete C120. You can see that actually we had a large scatter So for the same load level, you may have a couple of hundreds of cycles, or you also may have more than a million cycles. And here are the results for the concrete C80. We tested here 3 load levels, and 2 of our experiments from the load level 75 did more than 10 million load cycles without failure. So here we come to conclusions. We observed 2 failure modes. The first is combined push-through splitting failure in all monotonic and most cyclic tests. And we observed a pure push-through failure mode in few cyclic tests of the concrete C120. We also noticed that splitting cracks have a direct impact on the bond fatigue behavior, and they accelerate the bond fatigue failure, like we saw in these graphs. Finally, the formulas for the bond strength used in the FIB model code underestimate the actual bond strength between high-strength concrete and steel rebars subjected to push-in loading. That was all from my side. Thank you all for your attention.
Thank you very much. So the floor is open for question. I think there is a first comment and question from Abraham Danziger. Thank you for the interesting presentation. Did you have stirrups within the bonded part? And it refers to slide number 4.
Yeah, actually we had, as I showed here, we had 2 stirrups in the case of bond length 2.5 ds and 4 stirrups in the case of bond length 5 ds.
And so do you consider it provides some confinement that can affect your results?
Of course, the confinement level is important, and I mean, without these stirrups, we could expect earlier failure in the bond, or failure with lower loading levels in the monotonic case.
And so that's my comment and question. Do you consider having variation in the covered depth to bar diameter ratio so that you can finally obtain a pure bond failure mode and not a mix?
Yeah, exactly. You mean by increasing this cover,
yeah,
you may one may reach the case where all the failure modes are just pure push-through failure modes, no splitting. Yeah, that's clear. But the idea here was that we try to make something similar to usual beams or usual structures, where you have stirrups, you have, set up somehow like this, with cover almost like this also.
Yeah, I had one comment and one question about the in your concrete designation. I understand that during the project it was C80 and C120, but I think it's somewhat misleading because of the mean strength that are 84 and 107, if I have correctly read, and that when I refer to the diagram, slide 8, where you draw the bond strength versus the compressive strength.
Slide 8. Sorry, the numbering here is different. So here's slide 8.
Maybe it's this one, because you have the compressive strength from 50 to 120, something like this. But could you draw what are the results below 50 megapascal? Because maybe not in the same configuration, but in something similar where you can extrapolate. Because I'm surprised, because in your results you propose a linear variation, and generally the bond strength is rather estimated as a square root function of the compressive strength. So I think we need a single function for all the domain.
Yeah. Actually, in this case, we just like that's why I didn't focus on this. This is just, I mean, a quick representation of these points. I know what you mean. Later on, when we have all the results from the biggest campaign that I talked about that we are performing at the institute, when we have all the dots, and so we can produce a more sophisticated formula. This was just me quickly to represent how they are on the graph.
Okay, so I have to read, I think, other questions from Ye Hongning. So in the relationship between concrete strength and bond strength, hydrostatic pressure and near bond zone play positive effect on bond strength. Have you considered the effect pressure of this pressure in your experiment?
No, actually, in this campaign, we haven't considered the effect of side pressure. However, my colleague, Mr. Bakhtir, will publish soon a paper that he also investigated this in a numerical model where he considered the case of side pressure.
Okay. So there is a question by Andriy Setyavan. In slide 13, the curve on the left shows an anomaly where the same stress level, so the y-axis, the number of loading cycles causing the failure spreads in the whole x-axis from few to million cycles. Do you have any comment on this? Was this result disguised by different bar diameter or bond length that you use for those specimens?
You mean regarding the scattering, the results, like maybe? I think he mean regarding the scattering.
He wants
Yeah.
to understand why there are, for the same number of cycles, sometimes it's only between it's about 0.75 and sometimes 0.85, and what's the reason? Is it only scatter, or do you have any other explanation?
Actually, this is just a scatter that is somehow usual in fatigue experiments for bond, because in concrete already, if you tested the concrete specimens, pure concrete, you will see also large scatter. But in bond that is 2.5 diameter, that means about 4 centimeters for the case of steel 16 millimeter. It's a really short bond, and yeah, it's normal. I mean, for example, in the results of Eligehausen, if you looked at his paper, you will also see sometimes a really large scatter.
Okay. So I have one short question. What was the loading frequency for the fatigue tests?
Yeah, it was 5 hertz in
Okay.
all of the experiments, except one, which is this one. This one took, like I said, more than 12 million load cycles. So we applied, as I remember, until 2 million load cycles, 5 hertz, and then we increased the speed or the frequency to 10 hertz for the rest of the experiment. So it would not last weeks.
Okay.
Yeah.
I will invite Professor Monotonic to ask directly his questions.
Yes, thank you. Thank you, Francois. Thank you very much for the very interesting presentation. I have, in one of the first slides, you have shown that the aim of this work is to investigate the behavior of wind turbines, right?
Yeah.
Yeah. And in this typically in this kind of structures, you have compression, tension, as you have shown in your slides. And here in this test campaign, if I understand correctly, you have only compression, right?
Yeah, exactly.
Do you expect that compression tension would change the behavior?
It could. This is actually a nice question, and it's a nice research topic for later research. If you did pull out, then push in, I'm not sure, but we may experience a bit different behavior.
Yeah. And what is the And what is the typical bond problem that you can have in this kind of structures? Is it related to splices, or is it related to the anchorage that you have between the mast and the foundation?
I guess it would be more like pull out or push-in failure problem in the bond, because I'm not very experienced how these structures are being constructed and designed, but I think the cover would be much larger than or larger than what we tested here.
And are there laps in between bars?
Sorry, what?
There are there laps in the bars?
In my experiments?
No, in these structures.
In these structures?
Übergreifungsstoße.
Yeah. I would guess so. I'm not sure actually. Okay. As I said, I'm not experienced in designing these structures.
Yeah.
But because maybe they are really tall structures, I would expect that, yeah, they could use.
And another question, your bond length is very short, extremely short, 2.5 bar diameters, which is really very, very short. Do you expect a different behavior when the bond length is much longer?
Yeah, of course. We tested the length of 5ds, the longer length to monotonic, just to monotonic loading. But now currently at the Institute, we're also testing these for fatigue loading, and we will compare these with the 2.5ds bond lengths and publish the results later.
Okay.
In other publication.
Thank you. Thank you very much.
Thank you.
For also a question, have you considered to put on the same graph some results on ultra high performance concrete, which may exist at least in the quasi-static domain? In fatigue, probably not so much, but at least to see if there is the continuity with the effect of the compressive strength on your bond strength.
Sorry, maybe I didn't get the question.
I wondered whether you were aware of the results on ultra high performance concrete in terms of bond strength that you could put on the graph to see if there is the physical continuity of tau as a possible square root of FC or something like this.
Yeah, you mean here in this diagram?
Yeah.
Yeah, and the question if we will produce.
I think if you propose a formula which relates tau b as a function of FCM, it would be useful to collect
of course.
all the possible relevant data below and beyond your the domain of your experiments to see if there is consistency.
Yeah, we may check this. Thank you for the suggestion.
I think we're still allowed 1 minute, and maybe some more if some other people in the audience have questions. I don't see any.
If it is not the case, we can end here this session.
Yeah, and I think.
And Marta, what do you think? Can we stop here? Yes. I would like to thank very much all speakers for their excellent work. Also for keeping the time. It was really perfect. Thank you very much. Very interesting presentations. Very well presented. Very, very nice slides. I'm very impressed by this work. I would like also to thank my François Toulmont and Marta Del Zoppo for helping me in chairing this session. Thank you very much. And I would also like to thank the audience for the many interesting questions. I have seen that I have the impression that the audience is very active, and this is very nice. It's very good, very interested, and very interesting very interesting question. So thank you very much. This is the last session today. We will continue tomorrow morning at 9:30 Central European time. I don't know if Farid, you want to add something for today?
It's too early for the virtual banquet.
Okay, good. So, and I will also thank you very much the organizer for their excellent job until now. This symposium is really very good. It worked very good. Thank you very much to the organizer. Okay, so I think that we can close this session. Francois or Marta, if you have something to add.
No, we agree with the closure of the session. Thank you, Aurelio.
Okay, thank you very much, and see you tomorrow.